Yeah, in this work we try to understand how humans move around in 4D space and interacting with objects around them. By 4D we mean the 3D space and the temporal dimension. A person may be trying to make tea here in this example, and they will go around in the 3D space, grabbing cup, getting water from the dispenser, and so on. So in this work we try to predict future interaction locations and body pose. The input to this model is an observation till a point of time for 30 seconds, and we predict future interaction locations and how the person looks like when doing those interactions for the next 3 minutes. This duration is significantly longer than all the other pose prediction methods that are autoregressive and predicts every next token. We discussed the key novelty in interaction prediction. We address where the 3D location of the interaction, how the body looks like when during those interactions. Is the person leaning on? Is the person bending over? And so on. This is different from prior work that focuses on 2D video anticipation or short-term pose prediction. We propose novel multimodal architecture for future interaction and body pose prediction. Talking about the data set, it is curated from EgoExo4D, and we use the ARIA glasses that was presented just now. We consider cooking, bike repair, and health scenarios in this work. The data preparation stage involves using object detection from 2D frames to obtain, and then using SLAM camera to lift it to 3D to obtain bounding boxes, followed by extracting body pose, and finally finding interactions. I'll quickly go over each of them. So the first step is these 2D SLAM cameras. We use DETIC, which is a state-of-the-art object segmentation method to extract segmentation mask from SLAM cameras, and then we use these SLAM cameras to map from 2D to 3D point clouds. Once we have those labeled point clouds, we convert top K segmented objects to 3D point cloud, and then we use density-based clustering to find these distinct objects. The overall goal is to create tight bounding boxes and to remove noisy point cloud predictions. The final step is to create oriented bounding box from clustered outputs. This is how the overall bounding box looks like in this environment. Next, extracting body pose, we use WAM, which was presented last year in CVPR. We remove extra detections using largest area and view consistency across multi-view views. The final step is to use ego camera location to place the person in the 3D coordinates. The ego camera is the ARIA camera. And this is how the person looks like doing the same activity. The final stage involves finding the intersection of the objects and the human pose to find the interaction. We also additionally use EgoExo4D narrations to filter out the noise and make sure the interactions are also mentioned in the text. And we repeat it for all narrations and all objects to detect interactions. And this is how an interaction looks like in 4D space. Yeah, using all these steps, we obtain clean data sets for training and testing. I'll very briefly go over the model, and then I'll focus more on the visualization. We encode, given the past observation, we encode all these prior observations into multimodal tokens, and then we feed this token into an encoder, an encoder and a decoder to obtain all future interaction locations, followed by poses. For pose, we observe that a single interaction location can have multiple poses associated with it. So that's why we use a conditioned variational autoencoder to learn these things. We show one example here from cooking. Note that the kitchen here is novel. We'll play the video. The current human pose is the past observation pose. And here are the future interaction location predictions and how the human will look like when doing those interactions. This is the first point. Our method correctly predicts the future interaction location and pose. And note that we do it all together. All the interaction points are predicted at the same time. Yeah, so our method predicts locations and poses across a 3D environment. I'll skip the second example. It's similar in a bike repair setup. And we compare against state-of-the-art method for both interaction, location prediction, and pose prediction. Yeah, we outperform all strong baselines by a large margin. Finally, the takeaways. We are the first work to enable future interaction prediction. We use past observation video to predict interaction location and body pose. And we curate an interaction dataset, and our experiments show significant gains over prior work. Yeah, that's all. Thanks. This talk will again be, the poster will be on Saturday afternoon, so please drop by there as well. Thank you.
Thank you. The next presentation we have is EgoPressure, our data set for hand pressure and pose estimation in egocentric vision. Here you go.
So good afternoon, everyone. This is my pleasure to present our recent work, EgoPressure, a data set for hand pressure and pose estimation in egocentric vision. So, okay, thank you. So before we started, I want to talk about the motivation of the creating of this data set. So I believe that all the user of the AR/VR device has the same experience. So when the user want to text something in the VR device, it will become very difficult. So that means the finger always floating in the midair. So the simple idea here is to attach the virtual keyboard to a rich surface, for example, like a wall and table. But once we do that, it's very essential to estimate the pressure or the contacts when the finger, where and when the finger contact with the table. So, and then with this purpose, we could explore the relationship between the hand pressure and hand pose, and also visual appearance of the hand. So it's possible to, for the further application, it's possible to understand the hand object haptic interaction in virtual environment. Also, with the most important thing, we could enable the haptic aware detectors manipulation of the robotic hand from the human learning from the human interaction. For example, their robotic hands could crush the cola can, also could hold the egg. But it's only possible if the robotic hands could sense the pressure or could sense the force that's applied on the object. So what do we do in this project? So we create the EgoPressure. It's the first high quality egocentric touch contact and the pressure dataset with 3D hand poses. Also, we developed an optimization method to annotate the hand pose from our multi-view capture setup. And in the end, we also propose the pressure former. The first model estimates 3D hands contact pressure as a UV map. So this is our setup, our self-developed motion capture setup. We use 8 Artery Kinect camera under 30 FPS, 7 as a stationary camera, and 1 with the egocentric camera. Also, we have our own solution, as you probably see here, the left bottom corner. We use active AR marker to tracking our head camera. And also, this overview of our data set. We have 21 participants. We have 6 male and 5 female, and 32 different gestures for both left and each hand. And all the camera operates under 30 FPS with high resolution. So totally, we have 4.3 million frames around 5 hours. So once we have the data set, once we have the recording, we need to annotate this data. So here we also developed a marker list and hand pose annotation across multi cameras. Use differentiable render, and probably you can see here this our annotation result on the there should be video here, sorry. As you can see here, this is our results on the egocentric view, and we have also seven views from our static camera. And here I want to mention the egocentric view is not included to the optimization. The mesh and the hand pose you see here is only reprojects from our annotation pose via the camera via our tracked camera pose. And you could see here the good alignment of this mesh could prove out the quality of our annotation, also our head camera tracking. In the end of our annotation, we also optimize the pressure on the hand surface, represented as a UV map, and we have noted almost all the frame here. We have different pose and various sequence. So, and at this stage, I want to discuss about the hand pressure, hand contact and hand pressure representation. So there first is the 2D pressure. It's directly projects an input image. There are no geometric aware. There are several previous work as pressure vision and the pressure vision plus predict the pressure from the input image and directly project on the image plane. So, sorry. So so another is the 3D object contact. Is the contact as on the 3D objects, but they require additional object inputs. And ours is we want to introduce here the 3D hand pressure. Pressure is represented as the UV texture map directly on the hand model. And here we also implement a pressure former. The first method estimates 3D hand pressure use transformer. And and people usually question whether this method could apply for the general objects. Generally speaking, no, but I see the potential. So here I want to show you some demo from the MetaQuest. Here, yeah. And you see here it's also sometimes it's also work with the answer objects during the training. Okay, so concludes but not so concludes. I want to say talking about the dataset and code release. And currently the dataset is already released. It's a 21 participant and 64 sequence entire format. And currently, I only provide the RGB. Sorry, it's RGB, not RGBD. RGB with 3.3 million image and around 2 terabits, and the codes for the markerless annotation and the pressure former will come soon. Thank you.
Thank you for the talk. So the next presentation that we have is estimating body and hand motion in ego-sensed world.
Thank you. Okay, hello. Oh, it's loud. Okay, hi everyone. I'm Brent. I'm a PhD student at Berkeley. I'm very excited to be at my first CVPR of my life to share our work estimating body and hand motion in ego-sensed world. And we did this with this wonderful team that you can see up here. Okay, so I'll just start with some motivation. Like a lot of people, the reason why I'm personally very fascinated with egocentric data is just this property where you're able to capture all this data that's uniquely rich in action, right? You can put on these glasses, do a bunch of things, capture videos you wouldn't be able to do otherwise. There's one kind of important caveat to me here, which is that these observations of action are actually only partial, right? There's someone wearing these glasses doing all these things, but you can't actually see the wearer as you're gathering this data. And so that's kind of the motivation behind our project, where we're trying to ask this question of, can we take sensors on these devices, Meta Ray Bans or these ARIA glasses, which maybe only have partial observability, and use them to extract more complete action information. So we're going to take as input, very concretely, two things. The first is on the left here, the device SLAM pose. So this is SLAM from ARIA or any other egocentric device. And on the right, we're going to take egocentric video, and we're going to use this for visual hand observations. And then from this, we're going to try to output a few things. It's basically just a complete understanding of the human motion and action. So this is body pose, height, as well as hand parameters. So here's example outputs from our method. And so we call the system for this EgoAllo because we're trying to take these egocentric sensing information and then bring it into an allocentric understanding of human action. Okay, so I'll briefly go over our system. There's only two parts. Step one is we're going to train a diffusion model that's conditioned on the SLAM pose. So this is like a head conditioned diffusion model. Familiar with EgoEgo or works like Bow diffusion, this is going to look very similar. So we're going to start with inputs, which is our SLAM poses. We're going to use it to condition a diffusion model. Diffusion model is going to output some local understanding of body parameters. We can take these local body parameters, align them back to the SLAM pose, and that gets us basically the output in the format we want, which is global human motion. And here's just some example outputs of the system so far. So this is just part one of two. Left is input, right is output. And the main takeaway here is we can go from this very sparse, partially observed glasses pose to some plausible distribution of what the human is doing. Okay, and now if we compare this to the ground truth, you can see that generally we can get the feet and lower body correct. Like you can interpret the gait pretty reasonably just from this glasses pose. But the hands are totally hallucinated, right? Because we're not observing them at all, we're just using this SLAM pose. And so that brings us to part two of our method, which is kind of a simple or straightforward extension. We take the egocentric video, we run a hand estimator on it, and then we use that for guidance of our diffusion model. And if you're familiar with like classifier-based guidance in like image models, it's kind of the same thing. And that gets us the system with two properties. First, we're producing, three properties. First, we're producing these like global human motion estimates. And importantly, these estimates are both conditioned on the observed head motion and also consistent with whatever the hands we see in the image frame are. And if I had more time, I'd talk about all these things that mattered. I don't, so I'll just list them. First thing that we found in our paper is if you're very intentional about how you condition the model, so how you parameterize the poses and geometry, if you consider some like invariance criteria, you can actually improve estimation a lot with the exact same training data. We also study how our model incorporates like kinematic constraints and temporal context implicitly. You can actually use this to improve your hand estimates. And then finally, we put a lot of effort into this like implementation detail, which is the guidance optimizer. So if you replace Atom or whatever the standard guidance optimizers are with this like sparse Leavenworth Markov optimizer, you can do this guidance very, very efficiently. And yeah, that's it for the method. I'll just end on some results. Most of these are from EgoExo4D, so this is like from one of the COVID sequences. If you see the Gaussian splat, so we're just incorporating the scene for like showing that we're grounded in the scene and it's kind of like geometrically accurate. These are all captures I did around the CVPR deadline. So that's the Berkeley West office. That's me with my deadline Diet Coke. And then more EgoExo4D. More, I think we've looped. Okay. And yeah, that's all I have. Thanks so much for listening. We have a poster tomorrow, 4 to 6 p.m. We'd love to see you there, talk about our paper. And there's also the website. Thank you.
Thank you so much for the talk. The last talk we have for this session is online episodic memory visual query localization with egocentric streaming object memory. So do we have the authors to present?
Hi everyone, I'm Rosario Forte from University of Catania, and today I'm going to talk about our work in collaboration with University of Udine, which is online episodic memory visual query localization with egocentric streaming object memory. First of all, let's talk about episodic memory. the first definition of episodic memory was given by Handel Talving as the ability of an individual to recall personal information enriched by time and space context. For example, remembering a childhood experience or remember where we left an object. From this definition, the Ego4D dataset defined the episodic memory task as the task that requires localizing where in a video an answer can be seen. And from this definition, three declination of the task was given, which are visual query, language query, and moments query. Talking about the visual query localization, imagine that you are wearing your AR glasses during your day and acquiring with the glasses the whole day. Then, at a certain point, you want to retrieve one object that you have seen during the day. So you take the egocentric video, the patch of the object, and search in a video for this object, obtaining in output the spatio-temporal bounding box about the last occurrence of the object in the video. But this definition has some cons. The first one is that the visual query is known a priori. The second one is that different queries lead to reprocess the whole video, and wearable devices cannot store in memory a day of recording. From these problems, we redefine the task in an online manner, so same settings you are acquiring with your glasses, but this time you save in advance possible queried object. So you are doing your chores and so on, and at a certain point you build a high-level memory, so you populated your memory, and then when a query occurs, you can just ask your memory to retrieve the last known location of an object. So actually, the pros of these methods are that we can operate without storing the entire video, it is memory efficient, and this is scalable. To tackle this task, we propose our method, which is egocentric streaming object memory, and starting by a video stream with our object memory population framework. By tracking and detecting interesting object, we save this object in memory, and when a query occurs, we run the query retrieval, which reads the object in memory, and if there's a match, the spatio-temporal bounding box of the object with its last known location is given in output. So, just to give you some example from a frame, the object detector and the object tracker are run, and if there's any object in the frame, they are saved in memory. Then, if there's no object, nothing is saved in memory. And when objects are tracked, we save the same object, we save the representation of the object with the same ID. When a query occurs, since we have already built our high-level memory, we go back from the most recent entry in our memory to the last recent entry in our memory, matching the query with the object in memory, and then giving in output just the response track, which is the most recent appearance of the object in the video. We did our experiment in the Ego4D dataset, and actually our method, we did some experiment with state-of-the-art object detectors and object trackers, which are grounding Dino and YOLO for the detection and Mass and EgoStack for the tracking, obtain 4% of success rate, which beats the baselines, and less memory usage with respect to other baselines. Another thing that I want you to see is that with Oracle Detector and Oracle Tracker, success rate increase really higher. For this reason, we think that object detectors and object trackers are not yet ready to tackle this task, which is a downstream task of both. So, that's all. Thank you.